Hello, video on friction and how it works. Well, we've all experienced friction in our lives as we're walking along each day and we put our foot down and we push back with our foot. It's the friction that keeps our foot from slipping. If we're on the ice, the friction's less and our feet can slip. If we're riding our bikes and we put the brakes on, then the brake pad grips onto the wheel and that slows us down. So all of these things are going on, and in principle, we've therefore come across the idea that friction's a resistive force. What do I mean by that? It doesn't actually initiate any action. It's us walking, it's us pushing. That's the force, the motive force, trying to move us. The friction just sort of tries to stop us moving. It tries to slow us down. It's sort of pushing against us. So a lot of the time, in order to deal with these sorts of problems, we have to resolve forces, and that's what we're going to do. So let's have a quick look first at the research on friction and what it does. Well, a guy called Coulomb looked at this in the 1800s, and he found a couple of important things out. Firstly, that the friction is proportionate to the load that we put on. What do we mean by load? Well, usually it's the normal reaction. If we're standing on the ground, then our weight's pushing down, and effectively the floor's pushing back up at us with our normal reaction. So that's the load we're putting on. But friction also has a limiting value. Mu r, they calculated, because what they found is that when they did the experiments, there for a particular combination of floor and slippiness, etc., that we'd find this coefficient of friction. So, for example, if we were stood on ice and we put 100 newtons onto some ice, the friction would be limited to 0.05 of that 100 newtons, so it'd be 5 newtons, yeah? That's the maximum the friction could be before we started to slip. Now, that's, as you can imagine, that's quite a low level, isn't it? We all know that on ice we slip easily, and that can be unhelpful or helpful depending whether you're skiing. The other one is if we're driving our car, we want the rubber on our tires to grip on the floor, don't we? We don't want it to spin, we don't want to slip and skid. And in that situation, the coefficient of friction is quite high at 0.9. So if we had 100 newtons bearing down on it, the maximum friction we can have will be 90 newtons. So that's really high, isn't it? So there is a limiting sort of level of force, and each sort of material combination has its own coefficient, and we sort of pick them, don't we, to make sure we either got something slippy or we got something that's grippy, depending on our circumstances we want to use. So, and in principle, friction resists movement. So if we've got a very small force moving us along, the friction will only balance it out, and it will increase as the force trying to move us increases until it reaches this maximum mu r. And once moving, the friction can't increase beyond the mu r, so it just stays at that maximum value. Now, that's what they found in all their research. So let's see how we can use that in practice with an example. Okay, I've got a box being pulled along the floor by a rope which has got tension T. Yep, so it's trying to pull us in that direction. So as a result of being a rough floor here, there's a frictional force which is trying to resist that movement. Yeah. So, and when tension is the tension pulling force is small, so the friction's small and balances it out. Yeah, it purely balances it. Friction doesn't get bigger than the force that's initiating it; just resists it. Yeah. So that would happen, and as we increase the T value, so we increase it, we get to the maximum value, and it's still stopped. And what we think of in these terms is there's some sort of limiting value, limiting point, yeah? As we increase our tension, we reach this limiting point where the friction reaches its maximum, the mu r. And so now everything's in balance, and it's just before it moves. It'll stay still at that point. You pull it any harder, it'll start moving. So let's do some solving of the maths on this one. Well, if we resolve the forces vertically, we know that our normal reaction force here is going to be our weight, which is mg. Yep. So those two are balancing out going that way. And if we look horizontally now, then our tension that's pulling us along must equal our mu r. That's our maximum friction. Yeah, that's the mu frictional coefficient of friction, and r, there's our normal reaction force, sort of pushing down into the ground. And therefore, if I substitute the value in from above in place of r, I can find my limiting value is mu mg. What happens then if I increase the tension beyond this value that we just found? Well, the T gets greater, the resistive force is limited to its maximum value, the friction as mu r, and therefore I get a resultant force in this direction. Therefore I'm going to get acceleration in that direction. There's my little double arrow to go with it. So my resultant force is going to be T minus mu r. If I put that into Newton's second law as the F, and the F equals ma, then I've got T minus mu r equals ma. That means I can find out what my acceleration is with a bit of rearranging there. Get by making a the subject of the equation, and I get this form of equation. So the acceleration is T over mu, tension in the rope divided by m, minus mu g. That's our sort of frictional element, wasn't it? Once we've gone above it, there's our sort of maximum friction component there. Let's have a look at what happens if we're going doing the same experiment, except now we're on an inclined plane, we're going up a slope. So the tension's trying to pull us up the slope, friction's trying to pull us down. What's happened that changes here is that my normal reaction is going to reduce because my weight is pushing straight down, not perpendicular to the plane. So let's have a look and see what happens. Here's our force diagram then. First thing we can do is resolve perpendicular to the plane, and we can see that our reaction force, which must equal W cos theta now, because there's our angle, isn't that? There's our angle. We're looking at the adjacent side, so we're going to get the cosine. So that will be mg cos theta. So our normal reaction force is reduced. Now let's have a look going up the slope. That's what we're trying to do, isn't it? The rope's trying to pull us up the slope. So, and let's have a look at the limiting point. Our T is going to be T limit. Our friction will have reached mu r with our new value of r in here. So I can therefore get a balance at the limiting point that T lim must equal mu r. That's our normal reaction, creating the friction there, plus mg sine theta. So that's this component here of the weight pulling us down the slope. If I rearrange that, I can get this equation here. So T, the limit, must equal mg cos theta mu tan theta. So if you think about it, that mg, mu mg there, mu mg is what we saw in the earlier horizontal example, isn't it, for what friction would be, and now we've got some adjustments to that. And then if we increase our T further, then our box will start to move up the slope. There we go. So we've got acceleration going up the slope. We can work out what our resultant force is, which is going to be our T moving us up, subtracting the mu r, which has reached its limit, so it can't increase anymore, and our mg sine theta, our component of weight taking us down the slope. That's our resultant force. We can substitute that into F equals ma, and here's our equation. So T minus mu r minus mg sine theta will equal ma, And if we want to, we can now find our acceleration by rearranging this equation, and there we are. We see some similar things to what we saw before. There's our t over m, which we saw on the horizontal. That's the component we saw on the horizontal example, so that's now got cosine of it. But we've also got a new component here, which is that's the weight component down the slope. We do need to think about what's happening, which way friction's operating. So here I've got another example, final example, where our weight, there is no tension pulling us up, we've just got the weight pulling us down the slope. Now, if the weight's pulling us down the slope, that's the way it wants to go. The resistive force is going to be in the opposite direction, isn't it? Friction as a resistive force is going to be in the opposite direction. Okay. So this raises an interesting question, which is, at what point, if I increase the angle of this plane, at what point will this box just start to slip down the slope? That's quite an interesting piece of maths, so let's have a quick look. So again, we need to, at the limiting point we're interested in, our friction will have reached mu r, that's the maximum. We did the resolving of forces before, so we know in the last example that r will equal mg cos theta. Here we go. So that's what's happening in our force diagram. So we've got the component of weight going down the slope, we've got the friction trying to resist it. So at the limiting point, these will be in balance and friction will have reached its maximum value. So my w sine theta, that's my weight down the curve, which is, so mg sine theta will have reached mu r as our angle increases, and we can just do a bit of rearranging to see that sine theta from our left hand side, because the mg's are on both sides, so they're going to cancel out, sine theta will equal mu cos theta. And with a very quick switch, of course, dividing through by cos theta, we can see that at the limiting point, tan theta must equal mu. So when's it going to slip? Well, it's going to slip when tan theta is greater than mu. So let's have a think about this as a couple of examples. If we were stood on ice, our mu would be very low. So for tan theta to be greater than 0.05, we only have to get to an angle of about 3 degrees. So of course, when you're skiing, you'll slip on a very shallow slope. Yeah. Let's have a look at the alternate, if the one we looked at before, rubber on a road. So in our car tyre, if we had mu on a dry day is going to be around 0.9. Well, to get my tan to be greater than 0.9, I have to get pretty well up to 45 degrees. So your car would have to be angled up at 45 degrees for it to start to just slip down the slope, just skid down the slope, yeah, rather than roll. Okay, here you are then. Here's a summary page. I've set it out with the keywords at the top about friction being proportional to the applied load. That's R, that's our normal reaction, and its maximum value is mu R, giving you some examples of mu there. It resists movement and it will increase from a small value of friction, just balances whatever the motive force is until it reaches its maximum. And once its maximum has been exceeded, it just stays at that maximum value. So in my little diagrams below, for a small force, it's all in balance and nothing's moving. Gets to the point which it reaches its limit, where friction equals this maximum value mu r. That'll be the limit. But it will still be stopped, still be static. And then when the force increases beyond it, the tension, whatever the motive force, it keeps it moving, starts it moving in the direction of the motive force, and friction is limited at this maximum value mu r. So there you go. Hope that's of use.